Hey guys, welcome to another interesting video, and in this video I am going to discuss about a very common name reaction, and that is Birch reaction. Okay, so this Birch reaction is very much important for your general organic chemistry as well as for any competitive exams, right? And in this video I am going to talk about some unknown facts about Birch reaction which I think you will not get in normal textbooks, right? So this video will be very interesting. So what is Birch reaction? When you react any aromatic compound, I am taking this simple benzene for my first example, and you react it with, let's say, lithium in liquid ammonia and ethanol, or you can use sodium, you will get this non-aromatic product, right? So this is the Birch reaction, and this is the application of the dissolving metal, right? So what happens when you add lithium in liquid ammonia is that lithium give up one electron, and this electron is trapped into the cavity of the ammonia molecules, right? So they stabilize this electron, and the counter ion is lithium plus, and the reduction of ammonia by this electron to NH2 minus although occurs, but this is very slow, and if the electron gets any other substrate, it can reduce that. So in this case it gets a aromatic ring, and that's why it can reduce it. Now you may wonder that aromaticity is a very high energy, and why benzene should sacrifice its tremendous energy to reduce to a non-conjugated non-aromatic compound. Okay, so although aromaticity is a very high stabilization energy, but you shouldn't forget that benzene also, due to this high delocalization, it also has a low energy LUMO, right? And this electron is delivered to this low energy LUMO, and we can show it by this curly arrow. That first what happens, this electron goes here and form this, so this radical anion is generated. Okay, so you have this radical anion, and now you have your ethyl acetate. So this you have this ethanol molecules, and this anion is protonated by the proton from this ethanol, and it will form this neutral radicals, right? After that, another one electron can come here, and radicals are very much reactive. It is more so it will immediately form anion. Okay, so you are getting this anion. Now this anion I am representing like that, but it is not rigid. Okay, and you have this cyclopentadienyl anion, right? This is a stabilized anion, full delocalization is there, and surprisingly, when it takes another proton from your ethanol molecule, it gives you this non-conjugated product, right? But if this is a delocalized anion, you would expect that instead it will protonate from here, and you should get this conjugated product. So your expectation would be like this, but in reality what happens is that you don't get this product, instead you get this product. Now why you are getting this particular regio selectivity, it is not explained in most of the textbooks, right? I find many textbooks that they don't describe why this is actually occurring, and to explain this fact you have to consider the molecular orbital concept. Okay, so what is the explanation is, so if you look, so before discussing this fact, I would like to show you another example, that when you have this type of system. So this is another delocalized system, right? This is actually this one. Okay, so this anion we can represent like this. This is also 1 2 3 4 5. This is a pentadienyl anion, not cyclopentadienyl, but it is a pentadienyl anion. And when you alkylate it with methyl iodide, in this case you are getting this product. So 1 2 3 4 5, so methyl. So this product you are getting as major, and another product you will get also. So sorry, so this product is minor, so this is minor and this is major. So this implies that the conjugation, the formation, the conjugated structure, as it is more stable, it is forming in this case. And so you can say that the conjugation has a power to drive it toward this product and not this. So this is not, it is not that this product is not forming, it is also forming, but it is minor and it is major. But in this cyclopentadienyl anion case, it is shocking that this product you will not get and you will entirely get this product. So what is the difference here? And so if you consider this particular case and you do the molecular orbital calculation, you will find that the coefficient of HOMO is same at these 3 carbons, right? At these 3 carbons the coefficient of HOMO is same, and thus it can attack from any of the position with equal ease, right? So so all 3 positions are equal, and in this case the statistical factor is that there are 2 terminal position and 1 internal position, and that's why you are getting this terminal as major. And another fact is that this one is sterically terminal attack is sterically less hindered, so and conjugation is also there, so that's why you are getting this major. But in this case what happens is that you would expect that the same orbital coefficient should be here at these 3 carbons. So these 2 and this one, you would expect from the previous discussion that these 3 positions are same orbital coefficient, but in reality that doesn't happen. And why is this? Because in this particular case you can see that this we can label it C1, this is C2, and this is C3. Okay, so for C3 what happens is that its 2 neighbors are sp2, so it has 2 sp2 neighbors, whereas your C1 case you have 1 sp2 neighbor and another one is sp3 neighbor, right? And if their in the chemical environment are not same, then definitely their coefficient of the HOMO on these 2 different sites will not be same. And from the calculations, when you consider the effect of this sp3 carbon and so what they say is that this high CH bond overlap with this pi system. Okay, this is one type of hyperconjugation, and that makes this coefficient, HOMO of this coefficient is lower. So in these 2 positions the coefficient of HOMO is lower, and it is found that the HOMO of coefficient is higher at that position. And also when they form a radical like this, they study a radical like this, so you can again represent it by this full delocalization, and they calculated the charge density. They find that the most charge density is at this spin density. They say in computational term they call it spin density, so it has high spin density. So that implies that in this C3 position both the coefficient of HOMO is higher as well as the charge density is higher, and in this case these reactions, this protonation step, this is a very highly exothermic reaction, and that type of reaction is fully kinetically controlled. That is, the stability of the product doesn't matter. So it will totally dependent on the coefficient of the HOMO and the charge on that, and this both in these 2 factors this C3 wins over this C1, and that's why the protonation occurs in this position. And I can guarantee you that this explanation you will not get any textbook. For this you have to refer the book by Ian Fleming, Molecular Orbital and Organic Chemical Reaction. In this book you can find this explanation. Okay, so this is a very good, I find this and I think that I should share with you. So this is why you get this non-conjugated structure. So this is completely different outcome from a non-cyclic one, right? Now this is the case of simple benzene. Now let's say you have a aromatic compound where you have substituents, right? So you can have either you have a substituent like OMe group, so this is electron withdrawing group, and in this case when you add electron, what will happen? So two cases can occur. Either it can attack here, it can attack here to give you this OMe dot, or the electron can also attack here, and then what you will get, you will be getting this. So in this if I consider the red pathway, you are getting this particular case. So here you have dot and this negative charge. Now you have to consider the stability of these two intermediates, and you can clearly see that due to the presence of this oxygen lone pair, this negative charge will be destabilized, because this negative charge is facing direct repulsion from this oxygen lone pair, whereas in this case this negative charge cannot have this type of interaction, right? And that's why these will be formed, and first is this, then it will get protonated like the previous one. So you have two hydrogens here, and so one hydrogen H plus is added, and in the second, so one electron is added. So from dot it will be converted to minus, and you have OMe, and then again H plus from ethanol will come, and you are getting this particular products. Okay, so these we say orthometa. So when a electron donating group is in your benzene ring, like you can have OMe, in place of OMe you can have NH2 or NMe2, this type of electron donating groups when you have, you are getting orthometa product. Okay, so orthometa hydrogenation occurs, right? But what will happen in case of your electron withdrawing group? So let's say you have your carboxylic acid group, right? So first of all, in basic solution like sodium or lithium in liquid ammonia, it will be carboxylate anion first of all. Okay, and then when you add electron, again it can add either this position or it can add this position, and accordingly you can get this particular so you can get either so if you add electron here, you will be getting this anion, and if you add electron at the para position, you will be getting, so in this case you are getting, so para position, it can be stabilized into the carbonyl ring, carbonyl group, so you are getting this. And obviously due to this stabilization, this pathway will be followed and not this, so you will get this intermediate, because when electron adds to this para position, it can be stabilized into the carboxylate group. Okay, and this stabilization not present when it adds to the ortho position, and that's why this will occur. And after that, first here another electron will come, so it will have negative charge, and then both of these groups will be protonated, so you are getting like this. So here you have two hydrogens, and in this case you have OH, then tautomerization will take place, and you are getting this COOH, here H. So in this case, this position is called ipso, and this position is called para. So this is ipso para product. So this is the so if you have, instead of carboxylic acid group, you can have ester group, or you can have a nitro group. So there are two possibility: either you can have electron donating group or you can have electron withdrawing group, and according to that you have different regio selectivity. So for electron donating group you have ortho meta product, and for electron withdrawing group you have ipso para product. So this is the simple cases of Birch reduction. Now if you remember the product which we got from the previous case, that this OMe, okay, and they can give you further steps. So what will happen if you treat it with H plus? So it will be converted to this particular cyclohexenone. What is the mechanism? So you can wrongly write a mechanism like this. So you can push a arrow and say that this OM is formed, and after that your water molecules will attack here, and you are getting this particular product. Then you have acidic medium, so isomerization can take place and you get the conjugated structure, right? But this mechanism is wrong. This mechanism is wrong because vinyl ethers doesn't hydrolyze like this, and I discussed it in my other video. You can check it, the hydrolysis of ethers, but I am showing this mechanism briefly here. So what is the mechanism? So first step is same. First step is right, that this protonation step will occur. So you will be getting this oxonium ion you will get, but after that what happens is that the water molecule, instead of attacking this sp3 center, it will attack this sp2 center, because this attack on this sp2 center is much more favorable, and that's why you will get a tetrahedral intermediate, right? Then this tetrahedral intermediate can collapse, so you have proton source, and you will be getting this non-conjugated enol. Now what happens is that it can again undergoes enolization because it is acidic medium, and this enolization will give you this conjugated enol ether, which can be protonated like this, and that's how you are getting this conjugated cyclohexenone, right? So this example comes various time in your competitive exams, and this is very good example. And if you want this ether hydrolysis further, you can check out my that video. I put the link above. So this is the case of your Birch reduction. And another one point I would like to mention is that, so I showed you that in case of this type, so in case of your electron donating group like this, or you have NMe2, let's say like NMe2. So in this case, so this is, if this is your substrate, I said that you are getting your uh, ortho meta product, right? So but when you treat this with uh, weak acid, like if you don't permit it to go further towards that conjugated cyclopentadienone, then you can have a conjugated structure like this, okay? So if you do it, so how it will occur? It will occur like this. So first of all, it will be protonated from here, and so what you will get is that you will get this particular uh, OMe, and here H, right? And now you have double bond here. Now again, when this deprotonation occurs, when this enolization occurs, then it can either occur from this side or from this side, and you know that if it occurs from this side, you will be getting this conjugated structure. So that's how you get it. So it will spontaneously isomerize to it. If you have a trace of acid in your solution, you will be end up with this product. Although it is formed initially, you will get this conjugated one. And the very interesting case with this compound is that you don't get this compound in out of your Birch reduction. its rearrangement is so fast. So in case of OMe, when NMe2 group is there, its rearrangement is so fast that you will always get this conjugated product, right? You don't get this product because it's rearrangement, same mechanism, but in this case nitrogen is more electron pushing than oxygen because its electronegativity is less, and that's why the reaction is so fast that the rearrangement occurs and you will get this product. So this is the general discussion of Birch reduction, and I think there is nothing left to discuss, and if I get further complicated examples, I will obviously discuss with you, and hope this video will be helpful for you, and thank you for watching. Best of luck.